In this video, we learn about identity of a set. Suppose you have a binary operation star on set S, then an element E of set S is called the identity of the set S. Now look at the phrase identity of the set. So for a set there will be identity. If for all A belongs to S, we have A star E equals E star A equal to A. Basically, if you operate identity on any element, it has no effect. You will get the same element, A. Now look at example from the set of natural number with union with 0 and consider the plus operation. Then we know that if you take any number and add 0 to them, it will not get affected. You will basically get the same number. So 0 is an identity of this set W. Now we will look at some binary operation and we will try to find its identity. Identity may not exist as well. We will look at some examples of that as well. So we have two binary operations here, both we have already seen and we will see later as well. In first binary operation, x star y is xy minus 1, and in second binary operation, x star y is 1 minus xy. In order to find its identity, let E is an element in Z and consider it is the identity, and now we will use its property. Then we get x plus E minus 1. We will first apply x star E, then we see E star x, and we try to equate it with x. So we will use this binary operation, open this, we get x plus E minus 1. If we use this, E plus x minus 1 equal to x will get cancelled and E is 1. Since 1 belongs to the set of integers, so 1 is the identity for this binary operation. Okay. In second example, we will apply the same procedure to find the identity of this set. So we will take any element, consider E is the identity, then we will use its property or definition actually, and when we use this first part, then it will be 1 minus xc. If we open this star, we will get 1 minus ex and equal to x, and we will simplify this. You can see that since there are two equalities, it will result in two equation, and both side we actually get the same expression. And you can see that this expression does not always results in integers. For example, if you take x equal to 2, you will get e equal to minus half, which is not an integer. So this set Z with binary operation this does not possess identity. Identity of a set with binary operation is always unique. So if you have a set S with binary operation star, and suppose if E is an identity of S, then it is unique. It means that in set S, there is only one element which can be identity. Now, this is the first theorem we are going to prove in this course. So let's look at the structure of this theorem. Theorems are usually in mathematics if, then some hypotheses are there, and then there is then, and it will imply some result, something. So here we will look at the hypothesis. First thing, you have a non-empty set. This condition should be fulfilled. Second, you should have a binary operation. Third, you should have a associative binary operation. And sorry, this is not necessarily actually. And and the third one actually is E is identity. This will imply that E is unique. Okay, we can show that. So let E and E prime, this is a uniqueness kind of result. You have to show something is unique. So basically what you do, you will take two such thing with same property. Let E and E prime are the identity of the set S. Then we will apply the definition of the identity and we will get that since E is an identity, we get E star E prime E prime star E equal to E prime, because E is an identity, so we'll get E prime. Here we get E, and in and using this we will get E equal to E prime. Inverse of an element. Let S be a set with binary operation star and E is the identity. Then an element B is called the inverse of A if A star B equal to B star A equal to identity. So basically you have a set S, you have a set S and you have A element. B is called its inverse if AB results in identity. Inverse of A is denoted by A inverse, that is B is the inverse of A, then A inverse equal to B. Now take an example. Consider the set of integer with plus operation. We have 3 plus minus 3 equal to 0 and 4 plus minus 4 equal to 0. 0 is the identity of this set with binary operation. So if you take 3, then minus 3 is inverse of 3, and if you consider 4, then minus 4 is inverse of 4. In general, if you take any integer m, then minus m will be its inverse. Now we will show that inverse is unique in case of associative binary operation. So suppose you have a associative binary operation star on set S and let AB belongs to S such that B is inverse of A, then B is unique. Again, this is an uniqueness proof. So we will consider two inverses, B and B prime of A. Then B prime equal to B prime star E equals to B prime star, and this A will be replaced by A plus B. Now this operation is associative, so we can change this bracket. Now we will use this operation B prime star A. This will be equal to identity because B prime is inverse of A. Now E star B equal to B. Hence B prime equal to B. So we can say that inverse is unique. Now we will see a problem on finding inverse. So suppose you have a binary operation on Z. You have already seen this. We know that 1 is the identity of this binary operation star. We have already proved this. Now let y is the inverse of x. Suppose you have any element x and you assume that y is its inverse, then x star y equal to y star x equal to 1, and solving this equation we will get y equal to 2 minus x, and since x is any integer, 2 minus x will also be an integer, so this inverse belongs to z. For example, if you take x equal to 4, then y equal to 2 minus 4 equal to minus 2 will be its inverse.